Welcome to the class. Dear students, today we are going to discuss on nucleophiles and leaving group. So in this, first we will discuss what is nucleophiles, and then we will classify nucleophile, and then we will look at what is leaving groups, and then we will go for its classification, and we will learn to distinguish between good leaving groups and poor leaving groups. Lastly, at the end of this section, we will discuss the impact of nucleophiles and leaving groups in substitution and elimination reactions. So let us start the class, nucleophiles and leaving groups. So nucleophiles are, as the name implies, nucleophile means nucleus loving. What is it? Nucleus loving. So what species are nucleus loving? Those species which are rich in electron, they will go and attack the nucleus of an atom. Am I right? Nucleus is positively charged. So those species that are rich in electron, they are attacking nucleus. So they are nucleus loving. So nucleophiles are basically electron rich species. They are electron rich species. And what does it does? As I already said, they attack the positive part in a substrate molecule, or they attack regions of low electron density. Regions of low electron density. So these are the 3 points on nucleophiles. Let us rewind. The term nucleophile means that it is nucleus loving. Which species are nucleus loving? That which is negative in charge, or that which is rich in electron. Only they will go and attack a nucleus. So they are electron rich species, and as I already said, nucleophiles attack the positive part in a substrate, that is, they attack regions of low electron density in a substrate molecule. So as I said, electron rich species. Electron rich species. So what are electron rich species? What are electron rich species? They can be classified into two. The first is negative ions. Negative ions. Okay, example of this is halides, be it F minus, Br minus, I minus, Cl minus. They are all negative ions. They are rich in electrons. Okay, OH minus and Cn minus, they are rich in electron. Okay, carbon anions. Okay, they are also rich in electron. So these simple ions, simple negative anions, they are nucleophiles. Now there are neutral molecules. Neutral molecules, they don't have any charge, but they have a lone pair of electron. They have a lone pair of electron. That's what makes them nucleophilic. So they are classified as these neutral molecules. They are classified as oxygen containing and nitrogen containing. So let us see oxygen containing molecules. Okay, can you suggest some examples? Can you think out some examples for oxygen containing? Yes, H2O, right? They can donate pair of electron. They are neutral, like NH2, sorry, we are talking about oxygen, right? RCHO, RCHO, aldehyde, right? They can donate the lone pair of electron. What about RC double bond OR, ketone? They can donate a pair of electron. What about acid? RC double bond OH? Yes, they are all nucleophiles because they have a pair of electron. Even esters, correct? RC double bond OR, and esters, see, they can donate a pair of electron, right? And what about your ether? Yes, ethers also, all of them are nucleophiles because they have a pair of electron which can attract them to nucleus of another atom, correct? The second is nitrogen containing, N2 containing. Okay, they are also neutral molecules. Look at ammonia, look at primary amine, do look at secondary amines. And what about tertiary amine? all of them are having a pair of electron, and that pair of electron can attract them to nucleus of another atom, and that makes it nucleophilic. So we have classified nucleophiles into negative ions, simple anions, right? And we have classified it into neutral molecules. They have a lone pair of electron. So that can be classified into oxygen containing and nitrogen containing. And here we have completed our nucleophiles. I hope you have understood nucleophiles. Now let us see what are leaving groups. What are leaving groups? So we have studied that nucleophiles, they love nucleus, and the reason they love nucleus is they are electron rich, and being electron rich, as I already said, they love nucleus, they attack the positive part of the substrate, they attack regions of low electron density, and there we have seen the classification. Now let us look at what are leaving groups. Leaving groups. So a leaving group acts opposite to nucleophile. Acts opposite to nucleophile. How does it act oppositely to nucleophile? See, a nucleophile, it donates a pair of electron to make a bond with substrate molecule. It donates a pair of electron to make a bond with the substrate molecule, while a leaving group breaks the bond with the substrate molecule by withdrawing a pair of electron. So they act oppositely, correct? The nucleophile, it makes bond with the substrate molecule by donating a pair of electron, while the leaving group, it breaks bond. There was a bond here. It breaks the bond with substrate molecule by withdrawing a pair of electron. So that is a leaving group, and that is the difference between leaving group and nucleophile also. Let us now understand the types of leaving groups. Leaving groups are of two types. They are of two types. One is good leaving group. The other is poor leaving group. Poor leaving group. So what is good leaving group? Good leaving group is the species which can break the bond and which can withdraw the electron. It breaks the bond from the substrate molecule by withdrawing its electron at a faster pace. Correct? All of that happens very fast. That is a good leaving group. And what is a poor leaving group? Poor leaving group is a group that withdraws its electron, breaks the bond from the substrate molecule, but at a slower pace. So such groups are called as poor leaving group. Let us try to distinguish and identify. Let us try to find out the difference to distinguish between a good leaving group and a poor leaving group. Okay, how do we know that we are having a good leaving group or a poor leaving group in our hand? So the only thing that is important that can determine whether it is a good leaving group or whether it is a bad leaving group, the only thing that determines whether a thing is a good leaving group or a bad leaving group, the only thing is stability of anion. Stability of anion. Stability of anion means, what does it mean? See, this is the leaving group. Okay, so when it breaks the bond by withdrawing its electron, the leaving group becomes an anion. How stable is the anion? How stable is the anion? If the anion is stable, then it is a good leaving group. Its formation will be favored. So if the anion is stable, that means it is a good leaving group. Okay, its formation will be favored. Okay, good leaving group. The anion is to be stable. If the anion is unstable, like If the anion unstable means if the anion is reacting, okay, it's involved in vigorous reactions, rapid reactions, then it is unstable. Such a anion is, its formation is not favored, and that would become a poor leaving group. So an unstable anion is a poor leaving group. Unstable anion is a poor leaving group. Correct? So that is the only thing that identifies and distinguishes between good leaving group and a poor leaving group. A good leaving group, an anion, the anion should be stable. If the anion is stable, how do we form an anion? See, this is the anion. When the leaving group breaks the bond, withdraws the electron, it becomes anion. If that anion is stable, its formation will be stable and will be favored, and that would make it a good leaving group. If the anion is unstable, if it reacts rapidly with anything that it encounters, then it is unstable, and its formation won't be favored. That would make it a poor leaving group. Let us now try to find how do we find out whether an anion is stable or an anion is unstable. How do we find it out? For that there are some thumb rules, and you can say some facts. Based on that we can determine whether the anion is stable or not stable. Let us see those thumb rule. As a thumb rule, let's see the thumb rules. As a thumb rule, you can say that, let me rub the board. Okay, so there are some rules for this. As a thumb rule, you can say like conjugate base of strong acids, conjugate base of strong acid. What is the conjugate base of a strong acid? It's a weak base. That would be a weak base. Conjugate base of a strong acid is a weak base. The weak base means that it won't give its electron pair so easily. That means it won't react. So that makes that ion more stable. Stable anion. And if the anion is stable, then that would make it a good leaving group. Let us understand this statement by example. We take a strong acid. What are the strong acid that comes in our mind? HCl, correct? HF, right? And H2SO4, fine. Now let us dissociate them. Of course, it's a strong acid, it would dissociate. We don't need to do anything. Of course, yes. So these are the dissociating products, and H plus and HSO4. Okay, fine. All of these are acids. All of them will dissociate to give H plus. That is not important here. The important thing is what is the conjugate base. That is the important thing. See, this is the conjugate base that is formed. First case it is Cl minus, second F minus, and the third HSO4. This conjugate base, it is stable. The ion is stable. Had it not been stable, it would have been a reversible reaction. Is it a reversible reaction? No. It is only going on one direction, okay, towards the dissociating products. Had it been unstable, had it been reactive, it would have given its electron pair to H plus to make back HCl. Had F minus been reactive, had F minus been unstable, it would have reacted with H plus to give HF. Had HSO4 been reactive or been unstable, it would have reacted with H plus to give H2SO4. But does any of that happen? No. That means that these are weak bases or weak conjugate bases. Weak base means it won't give its electron pair, right? That's a Lewis base. So the Lewis base won't give its electron pair so easily. That means these are not so reactive bases. They are bases but not so reactive. They won't give its electron pair. And not reactive means what? That these are stable. These are stable bases. These are stable ions. So its formation will be favored. So that would make it a good leaving group. So that would make it a good leaving group. I hope you have understood this concept. What I have said here is these are all strong acids. These are its conjugate base. Are the conjugate base adding with H plus to give HCl back? No. Is it happening here? No. That means these bases are weak bases. Okay, these conjugate base are weak base. Base means, what is Lewis base? Donator of electron. That means it does not donate its electron so easily. So that means it does not react. That means that they are stable. So these are stable ions, correct? And stable ions formation will be favored. So they are good leaving groups. That is what I have said here. Let us understand the opposite scenario. Okay, we will understand the opposite scenario now. What is the opposite scenario of this? Yes, you guessed it right. Conjugate base of weak acid. Conjugate base of weak acid. Conjugate base of weak acid will be what? It will be strong base. That means the ion will be unstable. Unstable ion, and that would make it a, what it would make? Poor leaving group. Poor leaving group. Let us understand what I have written by using an example. We will see some very weak acids. The first weak acid that is coming to my mind is CH3COOH. Acetic acid is a weak acid, no doubt. It's a reversible reaction. CH3CO minus plus H plus. These are the dissociating products. The other thing is ROH, alcohol, very weak acid. You get RO minus and H plus as dissociating product. A very, very weak acid is H2O, right? And here you will get OH minus and H plus. Look at these. I agree, everything is emitting H plus out. They are dissociating to give H plus out. That makes them acidic. Of course, we are not saying about weak acid or strong acid, but acidic. It makes them acidic. The main thing is, look at the conjugate bases of these. Are they giving their electron pair back to H plus to form CH3COOH? Yes, they are giving. Is the alkoxide ion giving its electron pair back to H plus to become ROH? Yes. Is the OH minus giving its electron pair to H plus to become H2O? Yes. So that means they are strong bases. They donate their electrons. They can give their electron. They are strong Lewis bases. They can donate their electron. So that means they are strong bases, right? Look at this. They are strong bases. The conjugate base of weak acid is a strong base, correct? So they are all strong bases. Strong bases means that they can donate their electron pair very easily. Strong base means that they can react very easily by donating a pair of electron. So that would make them very unstable ions, very reactive and very unstable ions. Do you think the formation of unstable ion be favored? It won't be favored. The formation of unstable ion won't be favored, and that would make these groups poor leaving groups. That would make these leaving groups poor leaving groups. So that is how it comes up. Let me say to you one more time what I have said. Look at these acids. These are all weak acid. Acetic acid, alcohol, water is a very weak acid. It's almost like neutral. H plus of course is the dissociating product. Look at the conjugate base. I am saying that conjugate base is donating its electron pair back to H plus to become CH3COOH. Here also alkoxide it's donating. Here also OH minus is donating to become the reactant back. That means these are all strong bases. That means these bases are very reactive. Okay, they can donate the pair of electron and get involved in reaction. They are very reactive. They are unstable ions. Okay, that means the formation of unstable ion won't be favored. Correct? Right? So that would make it a poor leaving group. They won't leave so easily. Okay, from the substrate molecule. So that explains the first way to find out whether an ion is stable or not. Okay. What is the second way of finding it out? Okay, that is a question. So the second way of finding it out is by analyzing size of the atom. This is called as size versus basicity. Okay, we will understand that size versus basicity. Let us understand what it is. So this is the periodic table. Like this, it looks like this. Fine. So this is the periodic table. So there is it is seen that if you are going from left to right, and as you are going from top to bottom, the size increases. The size increases. So as an example, for this I take one series. I take halogens. Okay. So halogens, which is the smallest halogen? F fluorine. What after that? Chlorine. What after chlorine? Bromine. What after bromine? Iodine. Fine. So iodine is is the biggest of all atoms. Correct. Now let me consider its ions. This is fluorine, chlorine, bromine and iodine. Which is the biggest of all ion? Iodine ion is the biggest of all ions. Iodine ion is the biggest of all ions. And F minus is the smallest of all ion. Now this is the same charge as this. This is also negative, this is also negative. But the difference is that negative charge here is distributed over smaller area because F atom is small. So the negative charge here is distributed over a smaller area. So that has more power. This charge on F atom has more power because it is distributed over a very small area. So it can attract any positive species towards it. Correct? And it can donate the pair of electron easily. Correct? So that would make F minus strong base. That would make F minus strong base. So a strong base means that F minus would react very fast. So of course that would make F minus unstable ion. Unstable anion. Because it reacts very fast. It's a strong base owing to its small size. Okay, so it reacts very fast. So it is an unstable anion. And unstable anion's formation won't be favored. So that would make F minus a poor leaving group. Poor leaving group. Now conversely, just on opposite line is iodine minus. Here I minus. Look at I minus. What do you think about I minus? See, it has the same charge as F minus, but the difference is that the negative charge is distributed over a large area. So it won't be able to attract positive charge towards it. And there is less tendency to donate this electron and react. So that would make I minus weak base. That would make I minus weak base. That would make I minus unreactive or that would make it stable. That would make I minus stable. Correct? That if it is stable, the ion is stable, its formation will be favored. So that would make I minus a good leaving group. That would make I minus a good leaving group. So the order of leaving group will be like this. How? Which is the best leaving group among all? I minus is the best leaving group among halogen. Right? After that, Br minus. After that, Cl minus. After that, F minus. F minus is the least, it's the poor leaving group among halogen. Poorest leaving group among halogen. And the good leaving group, the best leaving group among halogen is I minus. is I minus, and reason I have already told and discussed. Let us complete the order. After F minus, it will be the chance of this acetate ion, because acetic acid is the it is the strongest acid, it is the strongest acid among all, so its conjugate base will be the weakest. Okay, after that alkoxide, after that hydroxy, and after that NH2 minus. So this is the order of leaving group. The best leaving group is I minus. Okay, and if you are going from right to left, you will see that the power of leaving group is descending or it is decreasing. So this is the descending order of the leaving group's capability as a leaving group. Correct? The best leaving group is I minus. The poorest leaving group, a very rare leaving group which does not leave so easily, is NH2 minus. All of these, you know, these things. From here you can start poor leaving groups. From acetate ion you can start poor leaving groups, and from I minus to F minus they are good leaving groups. They are good leaving groups. Right? I hope you have understood this section. You have understood this section. There is a third factor also, and that third factor that's, you know, determines the stability of ion is resonance. What is it? Resonance. Resonance. So this is the third factor. Resonance of anion. Resonance of anion. Now there are some leaving groups. When they become anions, they exhibit resonance. For example, consider RCOOH group as a leaving group. Okay, so when it leaves, what it would become? It would become this. Correct? And it would exhibit resonance. Right? It would exhibit resonance. Of course, this electron pair can go here and this can come here. So it will exhibit resonance. So the resonating structure will be like this. Now, such a kind of resonance, see, the negative charge is getting delocalized. So the formation of anion, is favored, and therefore carboxylate group is good leaving group. So we can determine if there is resonance, no, that would support the formation of anion, because resonance makes that anion stable. Correct? It would make the anion stable. So if the anion is stable, it would act as a good leaving group. So resonance also determines whether it is a good leaving group or bad leaving group. Fine. The main thing that determines is the first thing, whether it is conjugate base of a strong acid or conjugate base of a weak acid. That has more weightage. Okay. I hope you have understood these sections of what is a good leaving group and how to identify a good leaving group from a bad leaving group. Now let us understand the impact of nucleophiles and the impact of leaving groups in substitution reaction as well as in your elimination reaction. Look at the substitution reaction. First is SN2 reaction, which I am going to draw, nucleophilic substitution reaction. Look at this reaction now. This is CH. This is the primary alkyl halide I am going to draw. Right? This is a leaving group. This is going to leave, and suppose OH minus is the nucleophile. Fine. Now it should attack here. Backside attack would take place and we get a structure like this. Look at this. There is X here. OH would come here. Fine. In the next this thing, OH inverted product we will get in SN2 reaction. Do refer my video class on SN2 and SN1 reaction to understand this better. Now, what I wanted to say here is the impact of nucleophile and the impact of leaving group on SN2 reaction. See here, we need to have, of course, the first and foremost thing that determines whether the reaction will proceed through SN2 or SN1 is the nature of the substrate. Primary alkyl halide, if it is primary alkyl halide, it would follow SN2 pathway. That is okay. The second most important thing is the nature of nucleophile and the nature of the leaving group. Nucleophile has to be strong. Nucleophile should be strong. It should attack the substrate at a rapid rate. At a very fast rate it should attack. And leaving group, here X, it should be poor leaving group. Okay, why it should be poor leaving group? Because it has to wait till nucleophile comes and attacks it. Okay, only then this intermediates where atoms are arranged as spokes of a wheel, this intermediate can be formed. Only then inverted product can be formed. Only then SN2 reaction pathway will be followed. What are the criteria for SN2 reaction? There are two things. OH minus, that is the attacking nucleophile should be strong and the leaving group should be weak. Why? Because the leaving group, if it is strong, what would happen? Carbocation will be formed and that would lead for SN1 reaction. So the leaving group should be weak. Okay, it should wait till the time OH comes and attacks. Okay, only then it should go. So the leaving group here should be weak. Okay, that is poor leaving group. Poor leaving group means, what is it? Whether it should be a strong base or a weak base. It should be a, what is strong base, or it should be unstable. The anion should be unstable anion. Fine. So that is how it impacts the SN2 reaction. Similarly, you look at SN1 reaction. What happens in SN1 reaction? Yes, carbocation is formed. What is a step 1? See, this is the tertiary alkyl halide. We are going to say about SN1 reaction now. This is the tertiary alkyl halide. This is the tertiary alkyl halide. Fine. Now there is Br here, correct? Or X minus X here. What is a step 1? It occurs in 2 steps. This is step 1. Right? This is the step 1. Carbocation is formed. Okay. What is the step number 2? In step 2, OH minus attacks. It can attack from front side and it can attack from back side. Okay. Back side attack is much preferred and it occurs more. Okay. So we will get inverted plus retained product, but preference will be given to inverted product. Okay, all that you will understand if you are seeing my video on SN1 reaction. Here what I wanted to say here is, this is the step number 2. Okay, what I wanted to say here is the impact of leaving group. See, leaving group here has to be strong. Only if the leaving group is strong, it would form a carbocation. Correct? And attacking nucleophile should be weak. Only if attacking nucleophile is weak, it will wait for the carbocation to be formed. Fine. So for SN1 reaction to proceed, leaving group should be strong. The leaving group should be good leaving group. Good leaving group means, what is good leaving group? That it should be weak conjugate base. Okay, that is correct. Right? It should be a weak conjugate base, or it should form a stable ion. Stable ion. Right? So the X minus should be a stable ion. It should be good leaving group. Only then it will leave and a carbocation will be formed. Only then SN1 reaction pathway will be followed. And also OH minus should be, the nucleophile should be, let's write it as nucleophile. The nucleophile should be not so strong. Right? It should wait for the leaving group to go. Right? So that is how it impacts SN1 reaction. SN1 reaction. Fine. Now what happens in elimination reaction? Let us see that also, elimination in alkyl halide. Let's study about E2 reaction. So this is E2 reaction which I am going to show now. So this is our substrate which is a primary alkyl halide. Now OH minus, it has to abstract a proton, and X minus also has to go at the same time. So you get something like this, right? So CH2 double bond, CH2 you will get, and you will get, of course, H2O will go, and you will get X minus. This is E2 reaction, correct? So what we are seeing here, OH minus, it should be strong enough, correct? That is attacking nucleophile, it should be strong, and leaving group, it should wait for attacking nucleophile to come and attack. So the leaving group should be poor leaving group. It should be poor leaving group. The nucleophile should be strong. The nucleophile, attacking nucleophile should be strong so as to collide with this primary alkyl halide and knock out a proton. The leaving group should also wait, okay, for the attacking nucleophile to knock out a proton, so that should be also poor leaving group. So a poor leaving group and a strong nucleophile would favor E2 reaction. Would favor E2 reaction. So that is how it impacts E2 reaction. Okay, and now let us see even reaction also. Even reaction, how it occurs. So even reaction we can see here. So this is our primary tertiary alkyl halide, right? And what happens here, let me draw the full tertiary alkyl. This is also two steps. So we get a carbocation like this, am I right? Fine, we get a carbocation like this, right? In step number 2, what happens? What happens, OH minus, no, here the nucleophile, okay, I am writing it as nucleophile, it would attack and knock out a proton from here, fine, and this double bond, this pair of electron, it would come here. So what we will get is like this, CH3, we will get this product, fine. So here what is happening, the cation, carbocation is formed. So what we are expecting here, if the reaction is to proceed through even route, the leaving group, it should be good leaving group. It should be good leaving group. Only then this carbocation will be formed, correct? And the nucleophile, attacking nucleophile should be weak. Okay, it should not attack before it leaves. So the attacking nucleophile should be weak and the leaving group should be good leaving group. Good leaving group means what? What kind of base? What kind of, whether it will be stable ion or unstable? Yes, it will be stable ion, right? Stable ion means the weak base, weak conjugate base, right? So for reaction to proceed through even mechanism, the leaving group should be good leaving group and the nucleophile should have less strength, right? It should have less strength. So that is the influence of leaving groups and nucleophiles in SN1 and SN2 reaction as well as in E1 and E2 reaction. Dear students, I hope you have understood the class in a good way. If you have done so, please do not forget to subscribe the channel, and that would be a great encouragement from your side. Please do share and do like the video. Thank you very much.